Hello everyone! In this lesson, you will learn about security considerations respective to different parts of the RSA crypto system. This lesson will cover the prime factors selection and use, size of public modulus, selection of public exponent, and dangers of the repeated encryption with RSA. When talking about security of a cryptographic algorithm, each operation counts for its expected contribution to the overall security of the scheme and the potential vulnerabilities it introduces. Now that you know how to generate keys and decrypt with RSA, use that knowledge wisely. Countless developers have fallen prey to the apparent simplicity of this algorithm. And in this lesson, you will learn the meaning of the ingredients of RSA with respect to the security of the user, requirements on them, and common but not exhaustive pitfalls in the implementation. For ciphers like AES, generating a key means simply and quickly use a pseudorandom number generator to get enough pseudorandom bytes as follows. The RSA key generator algorithm is substantially more complicated, and many implementations have flaws. As the first step of the key generation, you need two large primes. This requirement immediately comes at a price. Not only do you need a secure pseudorandom number generator, but also a good primality test. A primality test is needed to relatively quickly determine whether a given large number is prime or composite without having to factorize it, for which no efficient non-quantum algorithm is known, as you know. The generate and test process runs until two distinct primes of the required size and not too close to each other are found. It is slow, and some applications concerned about the speed try to invent hacks at this step, introducing vulnerabilities. You can see that the time this just took is 4 orders of magnitude longer than the previous example of just getting random bytes. The product of these primes is the public modulus, which is the part of the public key of RSA. Apart from computing the modulus, the prime factors are also needed when you try to compute the Carmichael-Todian function for n to get the value lambda used in the next steps of key generation. Without the knowledge of initial factors p and q, given only public modulus n, it is computationally infeasible operation for big values of n. For instance, this example stops evaluation after 10 seconds, but you can try running it longer for yourself. Knowing the prime factors p and q, you can compute lambda and the private exponent d easily and instantly. Any other person or machine, given only public values e and n, to break the crypto system and extract the private key would first have to find the factors of n and use them to calculate the private exponent. This input, like the one before, stops evaluation after 10 seconds, and so the next input will not evaluate. The initial factors p and q have to be kept secret, and in practice are often destroyed right after creation, since knowing one of them makes computing the private exponent trivial. The public modulus n, the product of p and q, is recommended to be at least 2048 bits long to provide adequate security, which affects the speed of every future encryption. In context of RSA, the key size is the size of the public modulus. The complexity of breaking an RSA key is equivalent to the complexity of solving a hard problem of prime factorization of the public modulus. For a 2048-bit long key, the estimated level of security is comparable to 128-bit AES or 256-bit elliptic curve. An advantage of RSA against the growth of computational resources available to the attackers is that you can simply increase the key size and so the complexity of factorization, and remain protected for years to come. An algorithm that can efficiently factor an arbitrary integer would render RSA insecure. For instance, future quantum computers are expected to be able to defeat RSA with their fast factorization algorithms. Cryptographers around the world are already working on designing and testing of post-quantum cryptographic schemes. Since the size of the parameters greatly affects computation time, the public exponent is often chosen in a way that allows you to speed up encryption. A recommended value with a compact binary representation is 2 to the power 16 plus 1. It only has 2 ones in its binary representation. Nonetheless, several applications have used other values and have greatly undermined decryption security. For instance, if the public exponent is 3, an attacker can simply extract cubic root of the encrypted message to break it. And if the public exponent is 1, the encrypted message is equal to the plaintext, so it's not encrypted at all. Some implementations instead randomly generate a large public exponent and risk that its inverse, the private exponent, will be too small, opening the door for a whole new class of low exponent attacks. The way RSA was initially designed always produces the same ciphertext for the same message and the key. So if an attacker intercepts the same ciphertext multiple times, they will know it stands for the same message and try to guess it from context and structure. This approach was successfully used against Enigma during World War II, for instance. To prevent that, the plain RSA had to be improved by using padding to randomize the resulting ciphertext. The addition of padding has closed the possibility of guess attacks on repeated messages, but it has opened the door to attacks on the padding schemes. The pitfalls described here for RSA are an example of the dangers of all kinds of implementing any cryptographic algorithms yourself, for anything other than educational purpose. For practical applications, it is not recommended to implement cryptographic algorithms yourself, but to use well-tested software libraries like OpenSSL for this job. RSA in its full potential is supported in the Wolfram language, with the functions generate asymmetric key pair, encrypt, and generate digital signature. You can use RSA for both encryption and digital signature generation, depending on the application. The next lesson will introduce you to another asymmetric cryptography algorithm, elliptic curve cryptosystems.